Hi folks, this is CU speaking again. In the last video I presented you some monostable circuits made with the package 74123. Today I'm presenting you an alternative to that, an old package, the famous 555. It was invented back in 72, more than 50 years ago, by Hans Kamen-Zind. Despite the fact that he had a lot of other patents, over 30 other patents, he remains in the history of electronics for two things. For the famous 555 package and for a book, which is this one. Much Ado About Almost Nothing is a paraphrase. You know the original title anyway. That almost nothing is the electron. So for any of you who want to find the basics of the history of electronics, this is one of the best books to do. It stops anyway, doesn't give you many details about integrated circuits, but until then it gives you a lot of other details. Okay, so let's do the famous 555. It's a pretty small package, actually. It's a package only containing 8 pins, 8 terminals. As you may already remember, the logic packages, they contain 14 terminals or more. So this is not entirely a logic package because it only contains 8. Despite the fact that inside the package, among other components, there is also a bistable circuit. So before discussing the main topic for today, I just want to make sure that everybody understands when we refer to such a package, like such a dinosaur like 555, that the basic 3 applications it was intended for are the astable circuit or the clock generator, the bistable circuit or the flip-flop, and the monostable circuit, the one I'm going to focus on. So best for you to get this is to see all the 3 of them at work and to make the distinction before we focus on the monostable. Let's come here closer to see. So when I put the power on, like this, as you can see, without pressing any button, here you can see something switching the 2 LEDs at a certain frequency, which is about 1 Hertz at this time. 1 Hertz meaning 1 pulsation per second. This is called the astable. What does it mean, the astable? Once it's energized, it delivers pulses without pressing any button until you stop the power. So you put the power on, it starts to deliver pulses. This is called the astable. Now I'm going to use this. Because the buttons I have right here, they contain 2 things inside. They contain a touch button and an LED. So I'm using these 2 touch buttons to show you the second circuit, which is right here. I put my finger on it, which is in a configuration of a bistable. What does it mean bistable? It has 2 states. And you have 2 buttons to play with it. This button on my left is going to be the set, and this is going to be the reset. So when I press the set, this LED here connected to the output of the bistable, it's going to go on. Take a look. Set. You want to put it off back, you have to press the reset. So set, reset, set, reset. This is the bistable. And finally, this one here is another package which contains 2 555 packages inside, which is called 556. And you are going to see what happens is that if I'm only using one of them, let's say I'm only using the one having the LED in the bottom, what happens is when I'm going to press this particular button here, this one goes on, and after about 2.5, 2.6 seconds, it goes back off. So again, 1, 2, 2.5, it went off, okay? However, by connecting 2 of them together, cascading, when this one finishes the operation, is going to trigger the next one, you can connect or cascade 2 such circuits together, and this is what's going to happen. This one stays on for 2.5 seconds. When this one finishes, the other one goes on for 2.5 seconds, and it goes off. And of course, you can play with the duration of these ones as you wish. Why? Because we play with the formula. It's a very easy thing to do. And this is actually something like this. Remember, for the 74-123, the formula for the duration of one timer only, one monostable, it was given by 0.33 times R times C, times the resistor times the connector, the capacitor. So this was the formula depending on the inside diagram of the 123. But now, because we play with the 555, the formula is given by the manufacturer. So the original formula was 0.693 R1 plus 2 times R2 times the capacitor. However, if you take a look here, 0.693 is very close to 0.7. So given the fact that all the resistors and the capacitors, they have a certain tolerance, you won't be wrong. So I'm going to rewrite it here. The duration is approximately equal to 0.7 R1 plus 2 times R2. So times the capacitor. So this way, if you use that formula here, you won't actually be wrong because it's very close to the reality. Okay? So the purpose of using such a package, exactly like for the 123, is that by only playing with a couple of external components, 2 resistors and 1 capacitor, you can play almost at wish with the duration of the pulse. However, it's recommended that the resistors won't overcome 1 mega. Anyway, because we're going to make these circuits playing only with a couple of seconds to not waste our time, the resistors are going to be surely in the range. Then, this is for the astable circuit. So this is the formula for the astable circuit, but not for the monostable. For the monostable circuit, the formula is going to be 1.1 times the resistor times the capacitor. What resistor, what the capacitor, we're going to see in a couple of seconds. So, very short summary again. This is the astable circuit. As long as the power is on, you won't stop. So astable is equivalent to not stable. So this is a kind of clock generator here. Next is the bistable circuit. On, off, on, off. And next is the monostable or the one shot. Because you press the button one time, it gives you one shot. And you can also trigger a second one if you cascade 2 packages together, or you put only the package 74, you put the package 556, which contains 2 555s inside the same package. As you noticed, the 555 has 8 terminals. 8 terminals times 2, it makes 16. But because if you put them in the same package, you only need the power supply terminals 2 times. If you subtract 2 terminals out of 16, you have 14. So the 556 contains exactly 2 identical 555s inside. Then, for the fun of it, in order to exemplify these kind of diagrams, I took an old friend of mine here, an old tablet. And from this old tablet of mine, I have here an old application called EE Toolkit Pro. And when I press it, I have several kinds of things I can use for calculation. This is very useful for beginners. And if I press the 555 here, I'm going to find out several kinds of things I can use about the 555. So if we take a look, I'm going to put it here, a classical astable or clock generator, and you can see here the simulator of it. Okay, and in the simulator of it, you can see that the duration of the time it's taking for both LEDs is approximately equal, exactly as you see here on the diagram. This is because of the presence of this particular diode right here. And by the way, the 3 components entering in the calculation are the resistor R1, R2, and the capacitor C. So when I told you the formula, which was 0.7 times R1 plus 2 times R2 times the capacitor, these are the three components entering in the calculation. And what happens is, if I just remove from here, if I just remove the little diode, I'm gonna remove it quickly, like this, is this very little glass diode, is a typical switching diode 1N4148. You're going to notice that the lights right here, one of them is going to last longer than the others. So shorter, longer. This one lasting longer is approximately 2 times longer than the other one. And here I have the option in my simulator. Here, if I don't enable the diode, take a look, this one takes longer, and I'm going to make it exactly like mine. I'm going to make it 47 kiloohms, okay? So with 47 kiloohms, you notice that this one here lasts about twice longer than this one. This is because of the presence of the LED. It's not very relevant. This was the astable circuit, okay? If I'm going here for the flip-flop, the flip-flop is exactly the package here in the middle. And I said, if you press one button, it goes on. If you press the other button, it goes off. That's exactly like these ones here. I press one, it goes on. I press the other one, it goes off. It's a very good simulator for that. On and off, on and off. So this one is based on 2 buttons, 1 LED, and the package 555, okay? And finally, if I go for the circuit having 2 cascaded monostables, this one here, time 1 plus time 2, here if I choose a longer duration for the first one and a shorter duration for this one, if you take a look at the ratio between the 2 resistors, this one is approximately 4 times bigger than this one. So the duration of the time is going to be, if you take a look, for this one here, this one is going to be about 4 times shorter, okay? So the duration you calculate is 1.1 times the resistor times the capacitor. Where the resistors and the capacitor are located, where the pins 6 and 7 are related together, this is the resistor, this is the capacitor. And by the way, just a very short reminder of the terminals of the 555. The pin 1 is the ground, the pin 8 is the power supply. And by the way, as a rule of thumb, when I play with 5-volt circuitry, I usually use the 74123 as a monostable. When I play with 12-volt circuits, I'm going to prefer to use the 555 because the power supply, depending on the manufacturer, it goes usually between 3 volts and 15. I have a special package ZSCT 1555, which is starting at 0.9 volt power supply. This is made for portable stuff using only one AA or AAA battery. This is why the voltage goes so low. But usually, if you don't do this, there is a standard package 555 like LM555, which is based on bipolar junction transistors, BJTs, or like the one I chose for my experiments right here, the TLC555, which is the CMOS equivalent, okay? Now for this one, I repeat, is the pin 1 the ground, the pin 8 is the power supply, the pin 4 is the reset. If you don't need to use the reset, you're going to connect it to the 5 volt, because if you connect the 5 volt, you actually disable it. Otherwise, like in the flip-flop, the flip-flop circuit is going to use the reset here. When you press the button, as you can see, the 5 volt coming here on the pin 4, you press the button is going to short it to the ground. So when that signal goes down, you are going to reset the package, okay? Actually, you're going to reset the output. And by the way, the output is the pin 3. So now we know what is the pin 1, what is the pin 8, the power supply, what is the 4 is the reset. Pin 3, by the way, is the output. Pin 5. Pin 5 is called the voltage control. The voltage control allows you to modify the output frequency without playing with the two components R1, R2 or with the capacitor C right here in the oscillator. So without playing with R1, R2 or the capacitor. If not in use, the pin 5, which is the voltage control, you're going to connect it to the ground through a standard capacitor 10 nanofarads. Okay? It may go anywhere between 1 and 10 nanofarads. It's going to work just fine. If you want to control the oscillator by using that pin number 5, you are going to do one of the circuits called voltage controlled oscillator, VCO. I'm going to give you in the description of the video, I'm going to give you the address of a site of my friend Don Wilcher, where you can see an experiment made with the VCO. So at this point, we don't need to use the voltage control. So we connect it to the ground, we decouple to the ground through a capacitor. So we know now the pins 1, 3, 4, 5, and 8. Now the pin 6 is the threshold. The threshold is going to say that anytime the signal goes above 2/3 of the power supply, and the pin 2, which is the trigger is anytime the voltage goes below the 1/3 of the supply. Okay. So this being said, we know all the there is the pin 7 also. I'm sorry for that. The pin 7 is the discharge. So when the power goes off, it allows the capacitor C to be discharged. So next time the power goes on, the capacitor is going to start from 0. So now you have an idea about all the pins. The package is very nicely described in so many other sites. I won't insist on that. I just want to focus now on what? I'm going to focus on the monostable. So for the monostable, again, this is just the simulator. If I want to make this time a bit shorter, for instance, if I play with the resistor here instead of 470 kilo ohms, okay, I'm going to make it, let's say, to 20 kilo ohms. I'm going to make it 220 kilo ohms. So when I do and I press it, it's going to last much shorter than before. And this is going to be about twice shorter. I want to make them equal. It's no big deal. I can do this. And I'm going to make 120 kilo ohm each. So this way, they're going to last much shorter, both of them, you see? So it's going to last much. This is how you can play. And what's nice about this application, it also has the calculator. You're going to find online calculators. There are a lot of online calculators, but all of them are actually for the astable version, Very few of them are going to give you calculation about the monostable. And the monostable, again, is 1.1 times the resistor times the capacitor. Because I have two packages together here, I have two sets of RC, each of them controls 1555. Now, because I know it's going to be a bit difficult for the beginners to make the distinction between the connections 555 versus 556, I prepared here a little document. You're going to find both of them on Google Drive. I took the two diagrams, I took the 4 diagrams actually from the application. This is the astable, this is the bistable, this is the monostable doubled with the 555. But because I want to focus on the monostable, what am I going to do? I prepared for you a diagram where the 555, like in the original diagram of the application, both of them being connected together, you have the pin out. Both of them, they have the same pin out because the packages are identical. But what's nicer, what I've made here in the bottom, I translated this by using one package 556. The 556 again contains two 555s in the same package. And here is also the pin assignment, but for the 556. As you can notice, the pin 7 is now the ground, and pin 14 is the plus voltage, the positive voltage. And here in the experiment, I'm going to use 5 volt. On the second half of the package, there is no more connection for the pins of the supply because these two, they share the 2 pins of the power supply together. So you only have the functional pins for the connections. Okay? So To make these connections very easily, to understand how is this done, I'm going to show you what is the little trick about using the packages 555 and 556, okay? Because there is a little thing preventing you to use the 555 or the 556 properly, and I'm going to let you know. So here, what am I doing? I'm picking up the components. I'm going to dump them right here. Here is the package itself. This is a TLC 556, so a CMOS. The only things I prepared over here are some connections for the power supply and the push button I'm going to use in order to trigger. So one of the two things you have to consider when doing wiring around one of these two packages: do the connections with the power off. Never do connections with power on. They are very sensitive to the power on when you do connections. You may damage the package. So pin 14 is the positive, pin 7 is the ground. And then if I take a quick look on the diagram here, I don't need to use the reset terminals. So unlike the 555 where the reset is on the pin 4, this time for the first half of the 556, so the first timer, is going to be the pin 4 exactly like for the other one for the first half package, but it's going to be the pin 10 for the second half. So the pins 4 and 10, we just take a look here. The pin 4 is connected to the red line, which is the +5, and the pin 8, 9, 10 is also connected to the red line, which is +5. Obviously, this red line and that one are related together through this orange wire over here. So if I connect anything here, it's the same as connecting it here. So this is the only thing I prepared, okay? Next, what I'm going to do. I'm going to decouple the pin number, it was the pin number 5, the voltage control for the 555. Now I have the pin number 3 for the first half and the pin number 11. So for these two, for the pin 3, take a look what I'm doing. I'm just connecting a 10 nanofarad capacitor. So this little blue body is a 10 nanofarad capacitor. I'm going to connect it exactly on the pin 3 and on the pin 11 to the ground. So I decouple the two voltage control terminals because I don't need them anymore. Now, what's easier to also connect are going to be the two capacitors controlling the duration. I'm going to use here for the C1 and for the C2 10 microfarad. Maybe there is a little thing you should notice about them. Anytime you need a more accurate duration, you should use, like this one, a tantalum capacitor. The color of the body won't matter. This is a 10 microfarad, this is a 22 microfarad. So yes, the 22 microfarad is bigger, but the color, this is a light brown, this is a darker brown. They won't matter actually. They can color any color they want. So you have to notice there is a white line which is marking the positive, and the positive is going to the pin 1. So it's going to the pin 1, to the ground. And the same thing goes about the second capacitor. If I pick it up, this one is going to do between the pins 12 or 13 to the ground, from here to here. So just to make sure, you are going to notice that the pins 1 and 2 are related together. The pins 12, 13 are related together. So let me just place a little jumper over here. 1, 2 are related together. And I'm going to place another little jumper on 12, 13 because they are going together. So this way, the two terminals 1, 2 and 12, 13 are going together. So once you put the two capacitors, next thing you should do is to put the two resistors, 220 kilo ohm each, 220 kilo ohm. So one of them goes, as you can see here, between the pin 1 or 2 to the positive, the pin 1 or 2 to the positive. It's very easy, like this. And the other one goes pin 12 or 13 to the positive, 12 or 13 to the positive, just like that. Okay. So we've made a lot of connections already. Now, what also has to go is the triggering for the second package. It goes between the pin 8 and the pin 4, the pin 5, because the pin 5 is the output of the first, so you have to trigger the next one. Because of that, between the pins 5 to 8, you are going to connect this capacitor of 1 nano, just like that. And also, to trigger, you need a 47 kilo ohm. I have it over here. Even if you can't see the colors very easily because it's a darker body, it doesn't matter. So I'm going to place it between the pin 8 and the positive. So this is done. So now what's remaining to do? Two things: to connect the push button to trigger everything, and then what's happening is to have the LEDs connected. So then I'm going to connect the push button. It's over here. The push button, I'm going to need a wire from the push button. From here, I'm going to need it to the pin 6, just like that. So the push button is connected. Now I have to connect the LEDs through these resistors of 330 ohms. So one is going from the pin 5 because the pin 5 is the output. So from the pin 5, right here, is the output. I'm going to connect the other 330 ohms, which is this one, to the other output being the pin 9. So from the pin 9 right here, just like that. And then the two LEDs, I'm gonna see the colors right away when I put it on, because these are bicolor LEDs. So then I'm gonna be able to switch the color. So practically all the connections are done. It doesn't take long. It takes more or longer to explain than to do it effectively, okay? So I said there are two things to know about the use of this package. One of them was, don't make connections with power on. The power has to be off. And now I'm telling you the second thing you should do. Any of these two packages, they have a little drawback. They can propagate unwanted pulses if you have more packages to play with, so your project is more complicated. So in order to get rid of these things, you have to connect across the pins of the power supply 1 or 2 capacitors. I'm going to connect 2 just to make sure. One of them is a small capacitor. This is 10 nano. So it can be anything between 1 and 100 nanofarads. It's between pin 7 and pin 14, as you can see. 7 being the ground, 14 being the positive. And the second capacitor, to prevent the propagation for lower frequencies, which is an electrolytic capacitor, I'm going to use anything between 2.2 and 10 microfarad. This is 4.7. So I'm going to do the same thing in parallel with the other capacitor. So for the most of the circuits using the 555 or 556, at least one of these two capacitors has to be there, okay? Okay. 2.5 seconds here. and then 2.5 seconds there. You see? So remember this one in the top, 2.5 seconds the first one, 2.5 seconds the second one. So it's not a big deal actually to replicate this one. When you take a closer look to these monostables connected together, cascaded, it's exactly the same principle they apply in your washing machine. Whatever kind of cycle you choose, it's a sequence of operations. Each of them is timed very accurately. So here I only have 2 timers, but in a washing machine you have 3, 4, 5, 7, up to 7 timers, depending how many sequences are in the operation to perform. Okay, so one more time. Very easy to calculate the duration is 1.1 times the resistor times the capacitor. And what did we do so far? We made the distinction between astable circuit, bistable circuit, which was this one in the middle, and the monostables, even 2 of them connected together. We made the distinction, and we were also able to build any of them because this one was a bit more complicated. I prefer to focus on this one, 2 monostables cascading together. And it was very easy to do, as you could see. You just respect the connections and you're done. And additionally, it's easy to find all these schematics if you don't have the little application on my tablet, because you are going to find these diagrams on Google Drive with the link I'm going to put in the description of the video. Now, what's more about that? What's more about that is some interesting applications about the use of the monostables. The use of the package 555 in itself is absolutely unbelievable. There are hundreds of applications other people found already to use. So of course, nobody's going to be able to cover these applications in a short video. Now, I'm going to focus on this one. Let me shut the power off. I'm going to disconnect it. I don't need it anymore. The experiment is done. Okay. Now here, this is a project you've already seen last time. Then you're going to see that in the moment you put the power on, you won't see first 0, 0. You can see any combination. You see 9, 9. It happens to be the same 9, 9, but it's never 0, 0, or almost never 0, 0. And any professional counter should have this. So one of the nice applications of the 555 is what? It's something we call a power on reset. What does it mean? In the moment you apply the power on, one simple 555 is going to apply shortly a pulse to the reset of the counter, and this way you are going to be able to have the counter showing you from the beginning 0, 0. I'm going to have here some components, these ones, and we're going to build one monostable with a 555. So this is a standard TLC 555. I'm going to connect it over here. And then for the 555, we're going to have some connections. First thing I'm going to do, I'm going to decouple the pin 5 to the ground by a capacitor of 1 nanofarad, okay? Whatever I have available. So then, instead of using like here a push button to trigger, instead, I'm going to use a capacitor. So in the moment you put the power on, the capacitor is going to suddenly be charged by that resistor here in the top. So you don't need a button to trigger. It's going to be the capacitor charging, which is going to trigger everything. So if I'm going to connect this one, I'm going to connect it to the triggering, which is the pin 2. I'm going to put here a capacitor. It doesn't matter, it's not a tantalum one, because it has a leakage or not, it won't matter. It's just to trigger, it's nothing else. This one is going to be connected over here, the pin number 2. This is done. Then the capacitor of 10 microfarads is going to be this one, exactly like the one before. Is going to be connected between the pins 5, the pin 6 or 7 to the positive. And then we're going to have, I'm going to make it longer. I'm going to put a 220 kilo ohm resistor from the same pin here to the positive to charge it. Okay. Very good. So then from the output, I'm going to connect a 1 kilo ohm resistor, an LED. Don't forget the two things: power off when you make connections, and I'm going to place the two capacitors across the power supply. This time is the original 555, so my power supply is going to be between the pins 1 and 8. Okay, this is one capacitor, and I'm going to place a second one here, electrolytic one, between the same pins 1 to 8, like this. And now it's isolated from the counter, so it's not connected to the counter yet. I just want to check it first. Okay, so regardless what the counter does, I'm not interested. Okay, I want you to notice what happens to this LED when I put the power on. So let me just have less light. It gives a light for a limited time. I made it long because I want you to see it. Okay, maybe just to make it green. I'm going to reverse this LED because it's bicolor. Now it's green. So it lasts for a while. But what I'm going to do now, through the same exclusive OR I used last time, I don't want the power on reset and the manual reset to interfere with each other. So I put them at the inputs of a exclusive OR. So I'm going to put it on the pin 3, which is the output. And the output of the exclusive OR is going to go to the reset. So now take a look. Anytime I put the power on, it goes to 0. Anytime I put the power on, it goes to 0. So for the duration, I have it like here. I cannot count. But now, this is counting down. This is counting up. You see? I can reset manually anytime I want. That's another story. But when the power supply goes on, it's always going to 0. For how long? For the duration of the LED staying on. Ah, you want to make it very short. You don't want it to make it that long here. You don't want it to stay that long in 0. No big deal. You put the power off. You remove this 220 kilo ohm resistor. And you're going to put a much shorter value. Like this one is 22 kilo ohms. So it's going to be 10 times shorter than before. 10 times shorter than before. So we take a look. When I put the power on, the duration is very short now. You see? It's about 1/10 of a second. You almost have no time to press any button. But what you have to notice, the counters is always starting from 0. So that was a nice application of power on reset. How do you do this? With one monostable circuit. Okay? I'm going to disconnect this one. And I'm going to give you one last application. Here is one of my counters. There is a lot of circuitry here underneath. And I don't connect the sensors because I don't need to, because this one counts using sensors. Instead, what I'm going to do, right here, this module, take a look, is identical to that one here. It contains two packages, it contains two packages 556. So I have for each direction of counting, either up or down, I'm going to have for the synchronism of the sensors with the input module, I'm going to have two monostables for each direction. So take a look. I have a module made especially for that. So what I'm going to do, this time I'm using 12 volt. And in order to see what happens, I'm going to connect right here. I can connect one display over here. So let me just check the power for this one. Yeah, it's 12 volt. Very good. So the power is over here. These are the two legs for the power. Negative is black, then the positive. And then if I put the power on, you see it's always starting from 0. So I can count. I'm going to do just the simulation. I won't connect the sensors. I'm going to count up and down, no problem. I can count anytime. And here, if you pay attention to these two lights, when I press, take a look. Each of them is lasting for about 0.4 seconds. Okay? And if you take a look what happens, I'm simulating the use of the sensors. So this is for counting down, and this is for counting up. Is doing the same with the two LEDs. Take a look. This is for counting up. This is for counting down. So this is based on two packages 556. So a lot of applications can be done. I only showed you a couple of them, as my counter is made to use two displays. One of them can be put outside the door, the other one inside. So on both sides, you're going to see what happens. Okay. So you see, you can count up, you can count down. But take a look here. For the synchronism, with the signal was coming from the sensors. This is the application of the monostable circuits. With these ones, now we are ready to finally build what was the actual intention a couple of videos ago, the famous helper for the 5-second rule. So this is what we're going to do next time. Thank you very much for watching. See you next time. Bye-bye.